Thank you. Okay, hopefully everybody can hear me. I said if anybody had heard me speak, they probably realized I didn't actually need a microphone to be heard in a room this size, but so try not to blow you out. So anyway, I'm going to actually talk to you about something a little different than we did earlier. Actually, I don't have a solution for the problem that I'm going to talk about. I'm actually going to talk about some of the challenges that we have and hopefully look for how do we together across industries come up with solutions, because I think this challenge of putting powerful tools into the hands of non-experts is something that we have to do. It's not a simple thing to do, and it's not without the issues that we have. But I really do think that the culture change in many of our companies around how we do product design or manufacturing system design is dependent upon it. So hopefully, why should you spend your time here? Because all of you came here to learn something, hopefully, and your companies might even be paying you to be here. So I want to talk about why complex questions require sophisticated tools. Because one way to solve this problem is to give simple tools to people for questions, right? That makes it easier. Well, the problem is we don't have simple questions to answer. So that doesn't work very well. Talk about the fact that some industries, and I think this is true in many industries, that you're not going to have all your organization be simulation experts. A lot of them are going to be experts, but in something else. And so how do you enable them is a key thing. Understanding why putting those into the hands of others is a good idea, because some people would argue that it's not. I've heard those arguments. Understand some good and bad examples, and agree that a standard approach and toolkit going forward would deliver a breakthrough. And so I was fascinated by the teaser video we had this morning. All the stuff that was there was like, yeah, I want to do that now. Please give it to me. So we can talk about that later. Talked about who I am. I think the point here is you can read all that stuff, and you told a bunch of it already. Having half of my career being outside the simulation world, I think has been pretty important, because it told me about what really needed to be answered, what was really important. And so having had that experience first, and then becoming a simulation professional later in my career has really helped me focus on how do we drive work processes. And so that really is where my passion is at, is how do we use simulation in the way you guys are talking about? How do we do things quicker? How do we do things with fewer people? How do we do things in the way it drives innovation? And how do we do things in a way that gives, to the point made earlier, the consumer something they actually want to buy? Because we can do a great job of engineering and deliver a product nobody wants. Well, that's not helpful. So we also have to delight the consumer at the same time. And then there's one more thing that we have to do that the previous speaker didn't have to do, and that's we have to put it into the retailer's store at the right time of the year so that the customers can actually buy it. Because we have an extra layer. So we actually have what we call customers and consumers, and they're not the same thing. Our customers are the Walmarts and the Targets and the Costcos of the world, and our consumers are hopefully some of you guys out there. Hopefully some of you either shaved or brushed your teeth or some of those things this morning before you came. So technical expertise, just to give you some background, this is the first CFD problem that I worked on. So I did oiling, four-phase turbulent flow, and I think this was a torture test to see if I really was serious about learning simulation or not. But it also helped me understand, because it took me months to learn how to use this code. By the way, how many people in the room have built multi-block structured meshes? So you feel my pain. Okay, got it. For the rest of you who don't know what that is, be happy that you never had to do that. But the point here is this helped me really understand, because it took me months to be able to be productive in running these simulations. That's not okay today. We can't take months to teach somebody how to do simulations. They need to be able to do simulations in days or weeks at the absolute maximum. And so that's why this is my background. It helps me understand that. So what's our technical purpose for simulation? And it shouldn't be really different than what a lot of you guys are doing other places. It's about predicting and designing out failure modes. And those can be in products, those can be in packages, those can be in supply chains, those can be in manufacturing processes. That can be all the above. Problem definition. I know a lot of you are in automotive. And so this idea of modeling forces rigor is not a new thing for you guys. You guys have been doing this for a generation. Many other industries, this is not true. Many other industries, including mine, are highly empirical as our legacy. And so people do a lot of pretty black box experimentation. And so when people come to me and say, can you model something, I'll say, sure, I can model that. But I have no idea if I can answer your question or not, because I don't know what your question is. And so trying to build a simulation forces you to say, what's the question you're trying to answer? And so that's one of the things that we're still in the midst of that, and we're not unique at Procter Gamble in that. There are many industries that are still coming up that curve that's in a very different place than we are in automotive and aero. Understand the why of experimental results. We're still in a world where experimental and simulation are highly coupled. I heard it in Anand's presentation. In the electrical world, you guys are still there as well. There's a lot of things you don't completely have a handle on. So there needs to be a combination, smart combination of simulation and experiments. And then we need to do what we call designing in the first and second moment of truth at affordable cost. For us, the first moment of truth is when the person walks to the store shelf and decides to buy the product. The second one is when they actually use it. And so one of those things is it has to look good. It has to appear like something they want to purchase. And it has to work. It has to do both. Because, and I know this is important in the automotive industry as well, but people, how often do people buy a new car? Generally every 4 or 5 years. Our product, they repurchase it every month or two. And so if you do not deliver on the second moment of truth, they don't buy your product again. And if they don't buy your product again, we're out of business. So what we call repurchase is extremely important. And like everybody else, we want to ensure performance before we build stuff. And we need to do these trade-offs to get affordable. So my point is, our industry is really no different than others. However, there's also this part about the business purpose. We talked about innovation. Innovation is obviously extremely important because the requirements that the consumers want, whether it's for cars or whether it's for products for your hair or paper towels or whatever, is continually going up, and the competition is doing it. And so we want to find non-obvious solutions. We also can do a lot more trials than we can do physically. And I think everybody is aware of that. That's one of the great things about simulation. We can do cost innovation because everybody's cost conscious. Nobody wants to pay any more than they absolutely have to. Getting the insight from understanding how things really work over a wide range of conditions. That was one of the things I was really interested in Michael's talk this morning about understanding not just one condition, but understanding this wide range of what you're really going to see in the real world statistically. And because that's what our products are really going to run into. Variability is real. And it happens in every manufacturing process. It happens in all the use cases. We need to understand those things. And simulation offers us the ability to do that at an affordable price. Drive productivity. This is a big one for us. I think it's a big one for every industry. We just don't talk about it maybe as much as we want. But there's a constant need for everyone to be able to do more work. So eliminating time and dollar-intensive physical trials is something pretty important. We have a measure of net outside sales per full-time equivalent employee, and that's something that's expected to go up every year. Simulation is key to being able to do that. Speed. How many people here think consumer products like ours get put on the shelf between October and the end of December each year? Okay, none of them do, because 30% of the product in the store is changed for the holiday season. So if you're in consumer products, you don't get to put a new product on a shelf in that time. You got to fit into the window that Walmart and Target and Meijer want you. And if you don't deliver in that time, you're not on the shelf. It's that simple. So being able to get to market when you're supposed to is critically important. And we don't have 3 and 4 year product development cycles. We have 6-month product development cycles. So speed is critically important. First to the market is extremely important. Faster decision making is extremely important, and simulation helps to do all these things. And these are what the finance guys care about, quite honestly, and is extremely important. I would talk about a few failure modes. So this is a failure mode that we would rather not find out when you do this in the parking lot, because you also would rather not have us find out when you do this in the parking lot, right? And so this seems pretty simple. And actually, this is a fairly old capability for us today. But this is the design criteria for all packages that are larger than 2 liters. And so whether that's our products, whether that's antifreeze, whether that's whatever product that you go to the grocery store and buy, if it's over 2 liters, this is the design criteria. And there's 2 ways you can do this. You can either physically test it, you can do simulations, or you can just put a whole bunch of plastic in your bottles. But obviously that last one is not one that you want to do if you don't have to, because it's quite expensive. And also from a sustainability standpoint, it's not really where you want to be. So predicting this before you ever make them is an important thing that we want to be able to do. We talk about supply chains. We handle a lot of raw materials. If those raw materials show up frozen, that's a problem, because melting out a truck can take about a week. And if you're planning for that raw material, and if you want a reasonable supply chain, you don't want to have huge amounts of inventory. It's pretty important, especially when you have winters like we had here in the upper Midwest this year, or if you're shipping a sea container across the ocean with a very rare raw material. This is an important thing to be able to understand. By the way, this is also important for finished products in trucks, in cases. Some products are temperature sensitive. So you need to be able to understand, are they going to get hot? Are they going to get cold? How long are they going to be exposed to those conditions? And when you have literally tens of thousands of trucks of inbound and outbound on a monthly basis around the country, this is pretty important. And also we have very different supply chains around the world. As you can imagine, the North America-based supply chain is pretty different than the one we have in Southeast Asia, which is pretty different than the one we have in Central and Eastern Europe, which is pretty different than the one we have in South America. And so being able to predict this, because we make the same products in all these regions, is a pretty important thing to be able to do. And then process. This happens to be a mechanical process, but we could have had a fluid one as well. This is basically a high-speed manufacturing process for either diapers or our feminine care products. And essentially, you want to be able to put nice patterns on them, and you don't want to poke holes in them. And you want to be able to do it extremely fast. And so this is an interesting dynamics problem, which looks pretty easy until you add a material in here that I'm going to show you in a minute that makes it pretty complicated. And so the reason I'm showing you these guys is to get to this point of these are not simple problems. The dropping a plastic bottle full of liquid and getting, fracture criteria for plastic, that's a very, very complex problem. Yet we don't want to have experts running it every time we want to test a bottle shape. We want to have non-experts doing that. If I go back to this one, these are questions we need to answer every day for different supply chains. We don't want to have experts do these all the time. We want to be able to have non-experts answer these questions. Even this one is something, quite frankly, pretty routine in our product and process design world. We want non-experts to be able to do this, but yet the dynamics of this problem are extremely complicated. And so these are the things that we need to be able to do. Oh, great, we have sound on this one. This is pretty simple, right? Putting shampoo in a bottle, how hard can it be? Well, it depends on the fluid, right? And it depends on whether you actually want the product in the bottle or not, And because of the rheological complexity of this fluid, something as simple as putting a fluid like this in a bottle is actually quite complicated. And it's a very high-end tool. And it's not a high-end tool because we don't know how to do fluid flow. It's a high-end tool because of the rheological properties of these materials. And the fact that they have hysteresis, they have rate-dependent effects, and there's all sorts of stuff in there. So that's what makes this a complicated problem. And here's a couple of materials The one on the left there, that's a non-woven. You typically find those in disposable diapers or things like this. This is actually a simulation of toothpaste. And you say, well, who pours out toothpaste onto a flat thing? Well, nobody does, actually, or I hope not. But this is related to the properties of how you get in a tube. And the same properties that lead to that coiling effect are the same things that either make it easy or difficult to get it into a tube at the rate you want to get it in there, and actually have it in the tube, not all over the tube. It also relates to how you get it out of the tube and put it on your toothbrush in the morning. And it actually comes out of the tube and doesn't run out of the tube, or it doesn't, you don't have to squeeze it so hard you can't get it out. So these are some interesting material complexities. Again, these drive very high-end tools. And yet, these are routine questions that we want to have lots of people be able to answer on a regular basis. These are our engineering materials. We are really lucky when we get to work with metal. We used to have a joke in the one group that I led that said, can I please get to analyze a bracket? Because I actually know how to do that. And when the fact of the matter is most of the time we're working with polyethylene, which is a pretty highly variable product and actually has some fairly difficult properties associated with it. Or we're working with elastomers, or we're working with fibrous materials like this. And so a lot of our starting materials are polymeric films or fibrous materials. And this can be both for their structural or for their fluid handling properties. Structural properties of this, if you want to build a simulation, is one of the most difficult problems we've ever done. And you go to ask people how to go do that, and they're like, oh, well, just use soil mechanics models. Well, soil mechanics models don't work because soil doesn't compress 80–90% during its use and during its manufacture. And so we actually had to develop not only test methods to actually measure those properties, but new numerical ways of describing how the material behavior that's basically a combination of a lot of things that are out there, plus some very clever things that some smart people in our company figured out how to do. But this is one of the things that makes our problems very complicated. And you have to, and just measuring this and getting it into a finite element formulation is pretty difficult. Getting it so it numerically solves is yet another problem. And then giving that to a non-expert so they can actually get an answer is yet a third. And yet that's something we need to be able to do if we're going to be able to drive innovation. So again, this is more of those things, so I'm not going to go into it, but just to give you an idea of all of these different applications where we handle these kinds of materials. Gives you an idea of a handful of things that we deal with in terms of polymers. We do have polymers that are both softening and hardening in these regions, and we design them that way on purpose for specific things we want to do with the materials. But simulating those behaviors and getting them right is actually a very complex thing to be able to do. And for anyone who's done that kind of finite element work, they know what I'm talking about. And polymers have this wonderful thing of having all these nasty things all together at the same time. And then when you add in post-consumer recycle, when you factor in the fact that I showed you plastic bottles. Most of you probably don't realize this, but most plastic bottles you buy today have 3 layers. There's the outer layer, which is typically virgin resin, which has the colorant in it because it looks nice. There's an inner layer, which is typically also virgin resin, which is in contact with the product, so you don't get contamination. Then whenever somebody says their bottles have post-consumer recycle in them, there's a 3rd layer in the center, which can be up to 70% of the bottle, which has the post-consumer recycle in it. The reason it's in there is because you don't know what's in it. And so it's sealed from the product and it's sealed from the consumer in the middle. But it's have highly variable properties, and so you have to be able to handle it. So there can be all sorts of stuff in there. Because when they do recycling, it's never you get just polyethylene. You get a few labels, and you get some other, there's some fillers that typically go into polyethylene as well. And so how much of each one of those you have can actually be very different. So you get these very nasty behaviors, and they're not even always consistent day to day. So you have to handle, it's that idea of handling variability again. Because when I'm handling post-consumer recycle, the specification for material properties on post-consumer recycle is about this big. Because that you get what you get. And if you want to put post-consumer recycle on your package, you have to be able to deal with that. And if you want to predict failure, you have to have the ability to measure and predict failure modes based on a very wide range of properties. So this again makes this a not simple high-end problem, but we want to do it every day with people who do other things. Fibrous materials, I talked about that, so I'll move on. It's just that you get these really cool things, and it makes sense once you think about it. The more you compress it, the shear stiffness goes way up because these things can't slide by each other. But it makes for some interesting material models to describe the behaviors, and it provides a great innovation capability, because once you can understand and predict it, then you can use it for product features. This is an example of a pretty typical material that we would have in the fiber area, where you can compress it that much and you want it to stay that way. And if you can read the fine print down here, you can actually figure out what that's for. This is actually a process for making tampons for feminine protection. But you want to store that energy because in use you want the product to re-expand. So you can't have that strain be permanent. And so locking that in and understanding it and being able to predict it and use that for product design is a pretty interesting problem. I'll just leave it at that. Fluids also. You said, well, you have hard structures, guys, that, structural mechanics. Okay, I get that. Well, fluids ought to be easy, right? Well, it depends on. This is actually a surfactant solution. This is some velocity profiles that we've done actually with NMR imaging. This is kind of what you would hope to see, stuff flowing in a pipe. You can actually predict pressure drop because you have a continuous velocity profile. Look at this guy. Once I put salt in there to modify the properties, now all of a sudden I have a shear-induced phase transformation. So I have a discontinuous material that I'm trying to predict the behavior of with continuous equations. That's a problem. And so with this material, I can't even get pressure drop in a pipe right. Cannot even predict that until I had the ability to measure this, and now that we've developed the ability to simulate this. So I'm gonna move on from this, but I guess my point I want to get to is for what people think are relatively mundane products, and for what seems like maybe pretty simple problems to answer questions to, material behavior can make those very, very, very complex, and can require some very high-end capability to be able to simulate. So the bottom line out of all that is we do have very high-end problems. We need powerful solvers. We need sophisticated boundary conditions, settings, solution methods. A lot of these are highly nonlinear problems, so the solution strategy for even solving them is not just fire up the solver and let it run. You oftentimes have to, what I call, sneak up on the solution and in the solution methodology. It requires a fundamental understanding of the underlying science. And I'm going to talk about this a little bit more, but this is why putting simulation tools into the hands of simulation non-experts is critically important. Because that last problem I just showed you with what we call shear banding, or that shear-induced transformation, you need somebody who understands physical chemistry and rheology to help you with that problem. You're not typically going to find somebody who understands physical chemistry, who understands rheology, and who's a simulation expert all in the same person. If you do, you want to hire them, because there's 5 of them in the world, but yet you want to enable other people who might be formulation experts or who might be engineers to use those tools. So that's why that thing is so important. You need to spread the best capability to the many to enable innovation. So, and I've talked about this, different physics, few experts. What this leads to in many industries, and I think consumer products has got this, other places do as well, I'm sure you guys do, but the breadth of science means that many of your engineers are jacks of all trades. They know a little bit about a lot of things. If you look at my own experience, I've done manufacturing engineering, I've done mechanical simulations, I've done fluid simulations, I've done discrete event work. I built stuff in manufacturing plants. That's part of the base of people that we have. That can be a disadvantage, or it can be an advantage. One of the advantages of seeing lots of things is you make non-obvious connections. You're like, hey, I saw that there and that there and that over there. What if I could put those things together? And you can drive innovation. So we actually don't see this as a problem. It's a problem for me wanting to give simulation tools to people. But from a company standpoint, this is an advantage. Because what it leads to is products like this. This is a product that basically combines, some of you have probably seen this. This is a product that is made in a manufacturing line that looks much like a diaper converter. So the manufacturing process looks much more like making diapers than it does like looking detergent. But yet we put detergent inside of it. So it's a coupling of detergent making technology and diaper making technology. And not very many companies have people who do both. So by being jacks of all trades, you can make non-obvious connections. And that's what's called innovation. Work processes in many cases are pretty repeatable. So this is where having standards help, standard approaches. Access to high-end skills enables innovation. This one's in red on purpose. And this goes back to your video this morning and why I want your tool now, today, is enabling simulation non-experts, but people who are physics experts, chemistry experts, to access high-end tools in a standardized approach is invaluable if you want to go fast. It changes the culture and it changes how people learn. Managed workflows and automation is also critical because if you want to do it over, you want to get the data from a PLM, you want to put the data back into a PLM, you have to have this. And if you want to go fast and you want to know what you did and you want to be traceable, this particular product is not an FDA approved product, but we have a lot of FDA approved products. What this means is you have to have all your data, you have to trace it, you have to know where it is, and you have to be able to produce it if the FDA wants to see it. So all of this needs to happen. And this is a pretty complicated problem. So here's an example of just a routine thing that we do on a regular basis. And I want to ask yourself, do you want a simulation expert doing this particular thing? So here's something pretty simple. Pouring the liquid out of a bottle. Got to be pretty simple, right? Everybody does it the same, right? No, nobody does it the same. Everybody does it different. So this is just a handful of people and huge difference in terms of how they do it. Yet, we want to produce a package that people don't get stuff all over themselves or they don't dose the wrong amount, because if that's what happens, back to that second moment of truth thing, they won't buy our product again. So something as simple as, okay, I want to say, here's a full bottle, here's a half full bottle, and a bunch of other sort of things, so that this is the kind of plot that I want. Basically, from the time the thing is full till the time the thing is empty, I want the consumer to get the same amount of product in the same amount of time. Ideally, I want to make this as independent of angle as I possibly can. Ideally, I'd like to make it robust over a range of physical properties because I want to use the same package for multiple products. And yet, I don't want to have simulation experts doing this all day long because honestly, they're going to get kind of bored building this. And it's not a great use of their time. But if the guy who's designing the package can do this routinely, then that's a really big thing. Or even the people that are doing consumer studies can do this on a routine basis. This is a powerful thing. So I talked about this a little bit, but I think this is a business realities in many companies, especially smaller companies. Modeling and simulation is viewed as highly valuable But it's still seen as a tactic rather than a way to do technical work. You know, you guys talked about, you know, that it started out being a way to make sure you got your design right. A lot of places it's still there. I mean, it's still not fully integrated into the work process as much as we would like. You know, we have a lot of companies, ours included, that have historically been very empirical because of this complexity that I'm talking about. People say, well, this is too complicated to simulate. In some cases, they're right. In many cases, they're not. Many organizations have a fairly small number of experts. The big value comes when your experts can integrate the work in and it changes the work process. It becomes the preferred method. Automotive, quite frankly, has made that transition in most places. A lot of other industries have not, or are in the midst of it. In our particular case, we have both the advantage from an innovation standpoint and the disadvantage from a language and understanding of each other's standpoint of having many sciences. We need biologists, we need chemists, we need people with many different engineering disciplines, we need statisticians. Because of the types of questions that we need to answer, we don't, most chemists don't know a stress tensor if it hit them in the head, right? Okay, most of the engineers in the room here, are not good at doing chemical species calculations, or phase change calculations for complex chemistry. The fact is for what we're doing, we need both, and these folks need to be able to talk to each other. And that's something that's not a simple thing to do. And quite frankly, not all science disciplines are the same place on the journey to be able to simulation driven. Mechanical and chemical engineering are pretty far down that road. And it's because of the aerospace and the automotive industry that drove that transition, honestly. The chemistry world's not that far. And it's not because their problems are necessarily more complicated, it's because there hasn't been an industry focused on driving those solutions. That's starting to happen now, but it's behind. And so in many cases we still need physical measurements, but that needs to be coupled with simulations. So I put this slide in here because I know I've heard a lot of people say, you're not really going to give an expert tool to a non-expert. You know how dangerous that can be? Well, the alternative is, well, how dangerous can it be if they don't have the ability to simulate at all? So I know some people think this is what happens when you give a simulation to a powerful tool. And it can be. And I think this is the important part that I want to spend the rest of the time talking about. It's not that you're giving a tool to a non-expert in simulation. It's what tool do you give them to answer what question? Because they're not going to be able to do everything, but they should be able to answer very specific questions. And I think that's where the power comes in. And so this is the vision that we are working against. And I think this resonates with a lot of other people. And I'll let you read through that. But at the end of the day, it's really about how do I take things that a few high-end experts know how to do and give it to a lot of people in a way that drives a work process. A way that drives a work process. And a few of you know Tom Lang. This is one of his quotes. His point is that, a long time ago, if you wanted to fly, you had to be a pilot. Today, you don't need to be a pilot. You just show up at the airport. Many today, if you want to do simulations, you still have to be a pilot. We want to get to so you don't have to be a pilot to do simulations. I know that's an aspirational vision. I know we're not there today, but it can transform to you guys' marketing video where it can transform the way we do product and manufacturing process design. And it can be a competitive advantage for the companies that embrace that. So our key principles, I'm going to go through these pretty quickly. Easy and intuitive graphical user interface, ability to connect to supported databases, modular to allow for low cost, easy maintenance. I'm going to talk about this one a little bit more. If you notice the examples I gave, they weren't all structural mechanics. They weren't all fluid mechanics. They weren't, and there's some examples I didn't even give you. We do everything from molecule design using molecular dynamics to statistical and first principle based chemical mixture design. We do complex rheology. We do manufacturing process. We do packages. We do product design. We do interaction with the human body. Think of razors. And that's just getting started. We do chemical reactions. And so the point of it is we don't have one solver to connect to. We have dozens. And one of the problems that we have, and I'll show you a little bit this more as we go through, is most of the software suppliers, you guys included, have got a great solution for a narrow problem set. But I have about a dozen problem sets, and I really don't want a dozen solutions, because that doesn't meet my easy maintenance criteria. Execution time to be minimized. This is about real time as much as possible. So how do we enable engineers to be as close to real time as we can, or at least let them know that something's going on? Because I think, if you think how software is designed today, if the software is doing something, but it's not obvious that it's doing something, we have some way of telling people that, right? There's a bar that goes across, or there's something spinning. So at least that the thing isn't frozen up, is pretty important. We need to work on lots of supported systems. So PCs, Macs, this is one of our visualization technologies that we call pixel rooms. Best software for the task. So we might use SAS for statistical optimization. I did put this one in here just so to keep you guys happy. We might use gproms. We might use a number of different tools. Because again, back to the complex problem set. There's not a single tool that solves all of those problems. And there's a bunch I didn't even put in here. I mean, we do a lot. I was telling somebody earlier, my favorite tool of the week is Plant Sim, which is a factory floor discrete event simulation package that helps us make sure our plants are designed effectively. That's just classic industrial engineering that we do. And accessible from a lot of different places, because I really do believe that if I can give simulation tools to my plant engineers, I was one of them a long time ago, walking around on the floor with a tablet, I can change their world. And I can change the productivity of the manufacturing environment. That's something we can't do today. That's something that we need to do 5 years from now. And so this is a lot of little architecture stuff. I talked about most of this. This one is something you guys in automotive do a lot of. A lot of people outside of automotive and aero are just starting to do PLM. And so any way that you do all of this stuff needs to go get data from and put data back into what I call a structured database, or what we call PLM. I also think we need to have, whether you want to call it a developer's kit or something else, I don't know. You can call it what you want. But we need a common look and feel, because if I'm going to enable somebody to use a dozen different tools as a part of a work process and they all look different and work different, that's not good. And the software industry figured this out a long time ago. I mean, Apple started it with the original Mac. But if you think about the Microsoft Office suite, or any other suite of software, there's a premium on look and feel. Well, why is that? It's about productivity. It's people know where to go look. And if every one of these things is designed differently, that's not good. And it's also from a common maintenance standpoint. And you're going to hear me say maintenance probably more than any other word in this whole presentation, because when you go to putting these tools together, it's relatively straightforward to create a tool. It's very difficult to manage the life cycle of that tool on an ongoing basis, because typically it's created by the expert. The expert moved on, is doing something else now. Their interest in maintaining a tool is about this big. That's not what they do. I just put a thing in here very quickly just to show you this is not just about P&G. There's actually a state of Ohio consortia called AWESIM that's about how do I provide these kind of tools for small and medium-sized manufacturers. I'm not going to go into any details other than just to say this concept is out there for others, and if you want to go read it yourself, you can go do that. This just talks about what's in it for small manufacturers. There's this discussion about pay-as-you-go usage and other sorts of stuff. And so, but what this particular thing is about, a little bit different than what I talked about. I talked about, as a company, we're trying to enable non-experts for innovation and for productivity. This effort, because it's done by the state government, is about enabling non-experts for economic prosperity. How do we make small companies more competitive? Which for our country is extremely important. So this is not just something for the big companies. This is something for the infrastructure of our country that we also think is important. And so for the big companies that use small companies as suppliers, if we don't enable them to also have economic prosperity, they won't be around. And so our whole economic infrastructure, I believe this is an important thing. This is something that our company is a part of and is sponsored by the state. And there's several of these things that are going on. And so this is more than just about Procter Gamble, or in the case of the previous speaker, just about Ford Motor Company. These are economic considerations for the United States. Just a couple of things around where this all fits. In general, our work process, and I think most people's work processes fit this, you identify some kind of innovation breakthrough, you do feasibility testing, you do a bunch of optimization to try to balance all the criteria. You want to do all this stuff with simulation before you start on detailed design. And here is where enabling people that are experts, again, in physical chemistry, okay, I got the 5-minute signal there, are important. So this is just, I'm going to go through this very quickly. This is basically, if you have somebody who's an expert in mixing technology, processing of fluids, but not a simulation expert, this is a tool that we've created. And you can go through and do a bunch of stuff here. And then they can get this themselves. And I'm not going to go through these, but these are animations that they can go visualize. That's what what they get. And this is all done. We teach people to do this in about a day. And then they can go off and do this work themselves. For those of you who've been involved setting up a mixing simulation and getting it to run and getting useful information out of it, if you're an expert, even with today's tool, can take you about a week. We can set problems up in about 45 minutes now, and people have answers tomorrow morning when they come into work. That's what we want to do for all of our processes. And so there's the pretty pictures. And then they also get this plot. This is basically residual standard deviation. And so they can see here's how all these things they work, and here's the Reynolds numbers and a bunch of stuff. But anyway, so this is just looking at different options. Now I said an Ansys, so I figure I probably ought to put something from Ansys in here since I'm talking at an Ansys conference. I'll go very quickly. I was really happy to see that you guys got SpaceClaim because we were using it before. It's one of my favorite tools now when I occasionally get to actually do simulations. But the point of this is this is now easy. Because you can go over here, you can turn things on and off. You can seal, this is geometry extraction, guys, this is fabulous. For people who did it the old-fashioned way, this is awesome. I mean, all you got to do is you cap it off, you hit volume extract, and magic happens. I can't say enough about this tool. I love it. And now you're ready to set up and mesh, and this is something you guys created for us. And great, you get all this stuff, and now you have a simulation. This is great capability. However, here's one issue I have. All of this is custom scripts. Is there a toolbox that we can go create this? Sort of, but not really. It's still all custom scripting. So each one of these is a one of a kind. From a maintenance, from a documentation of how it works, when we go to a new version, how does it get upgraded? That's still a pretty clunky task to do that. It's a wonderful tool for the user. It's a not so great tool for the guy who has to maintain it. I'm not going to go through this one, but this is an example out of Plant Sim where you can compile executables. This is a pretty clever one actually, because the people can only use and change a handful of things in it. So where next? We, and I believe the industry, is going to more structured work processes. We have to, from the standpoint of productivity. Modeling as the how for many decisions. We're going to continue to populate that. Simulation tools embedded in a PLM or connected to it. Get data from it, put data back into it. and do that in a seamless way without the users having to spend all their time in the PLM environment. Enablement of the masses. And what I mean by that is I really mean people that are experts in their science, but not experts in simulation. A wide variety of tools, depending on the work process. Easy to maintain and upgrade. I know I've said that a bunch of times, but hopefully I got the point across. And then, so what do we need for that to be successful? I think we need a standard developer's kit, just like you have for these things. You know, the apps that are on here all work the same way, more or less. They all have a common look and feel, and they're written to a same standard. So maintenance is relatively straightforward. We know we're going to have a split interface and solve. I'd like to get to a single language if we could. And we need light bandwidth requirements. Because if I'm going to enable the engineer on the factory floor with a tablet, he can't be doing hardcore calculations on his tablet. They need to be remote, but yet he needs to get them right away, wherever he is. I think that's a pretty important thing for us to be able to deliver. I'd like to see common approaches across industry. I'd like to see us allow a wide variety of pre and post tools, a wide variety of solvers, but all in the standard interface. Because in my world, at least, I am not going to get all of the, unless Ansys buys up everything, which I don't think you're probably going to. I'm going to use tools from a variety of different suppliers for different industries and answer different questions. If my solution to give all this stuff to people is different for every one of those areas of science, it's going to be extremely difficult for me to lead the culture change I want to lead. So this is something I'm looking forward to, and something that I'd like to work with folks to become a reality, because I think it benefits not just P&G, but I think it benefits many industries, and I think it benefits the economy of our country as well. So with that, I don't know if we have time for any questions or comments or anything, but I'd be happy to field them if that's something that we have time for.